All right, how is everybody today? Okay, well, this is it. It's been a long time coming. This is the final week of the 2018-19 school year. So our plan today and tomorrow, we're going to try and get as far with this final lesson as we can. I'll definitely be able to show you circles, limacins. We'll talk about roses. I do. Okay, come on in, sir. And actually, Alex, I need you to go ahead and take your test for me. And Fawaz is taking the test. Now, you two can work together and you can use your notes. But on the parametric equation problems, make sure to simplify, like expand a squared binomial, all that good stuff. Okay. All right. Like I said, we'll be able to talk about definitely circles and limacins. In fact, I'll help you identify what type of limacin it is we're dealing with today. And tomorrow we'll graph maybe one or two, and then we'll go ahead and talk about some roses. Probably won't be able to graph any, but at least I'll be able to help you identify what's going to be happening, because there is a problem like that on your review. Speaking of the review, I'm going to give you Wednesday, just the class period, to go ahead and look at it, wrap it up if you've not already done so. Is there anybody who has not looked at the review yet for the final? Okay, that's good. That's good. And then you guys will take your final with me on Thursday, and that will be the last time I see you guys. Okay. All right. Any questions about what's going to be happening? No? Okay, then let's go ahead and get to it. Now, I created this sheet for you that has all the graphs that you could potentially, now, not every one of them, but the most common graphs, I'll say, when you start to look at polar equations. We have circles and limacins, roses. Like I said, we'll get a little bit to the graphs that we will not be able to talk about, lemniscates and spirals of Archimedes. At least, hopefully the name will sound familiar for those of you who are going to be moving on in mathematics. But what we're going to start with today is a pretty important concept when it comes to these graphs, symmetry. Because if you know the symmetry of a graph, well, then that cuts down on the amount of work you have to do graphing it. You'll see what I mean when we get to the end. But there are three types of symmetry that we're going to be looking at. There's symmetry with the polar axis. What's the polar axis? There you go. So we're talking horizontally, right? Okay, basically what we used to refer to as standard position. Okay, the line theta equals pi over 2. All right, well, that's vertical. Okay, so theta equals pi over 2 is right there. So these lines of symmetry mean that if I could take the graph and fold it along those lines, remember the two parts are going to come together perfectly. They're going to be mirror images of each other. In fact, last week we saw that if you're only given theta, if theta equaled an angle measure, that was always going to represent a straight line. Well, what if you were only given the radius? That would just be a circle. There you go. And then our final type of symmetry was going to be about the pole. What does that mean? Like, what's the pole refer to? There you go, what we used to call the origin in our Cartesian coordinate system. There we go. So let's talk about the first one, symmetry with respect to the polar axis. The test is simply to replace theta with its opposite, negative theta. If you can do that, simplify the equation and get the original equation you started with, well, that tells you that it should be symmetric with the polar axis. So let's take a look at our example here. R equals 3 plus 2 cosine of theta. Okay, well, I'm going to replace theta with its opposite. So R equals 3 plus 2 cosine of negative theta. We've actually talked about this recently. What kind of function is cosine? It's even. So what does that mean? What does cosine of negative theta equal? Okay, what's that, Aiden? Okay, so the negative basically disappears. Okay, so cosine of negative theta is just equal to the cosine of theta. Because if you were to look back at the original graph of cosine, it's symmetric with respect to the y-axis. Okay, but when we're talking about these polar equations here, this shows me that we're going to have symmetry with the polar axis. Well, if that's the case, the radius equals 3 plus 2 cosine of theta. See, I got back to the original equation, so now we know it has that type of symmetry. Okay, that's all there is to it. If you replace theta with its opposite and get the original equation. Okay, now you've got to do one extra thing when it comes to symmetry on theta equals pi over 2, you want to replace both the radius and the angle measure with their opposites. If you can do that, simplify, and still get the original equation, well, then it shows you have symmetry with theta equals pi over 2. Okay, just like this graph right here. Imagine that went through pi over 2. Or let me try that again. There we go. So if I were to fold along that vertical line, see, that's much better. The two parts are going to come together perfectly. So my equation here says r equals 3 sine of theta. Okay, so the opposite of the radius equals 3 times the sine of negative theta. Okay. What was the only other even trig function that we had? What was the reciprocal of cosine? It was secant. So remember, cosine and secant followed the same rule. They were even trig functions, so that means sine has to be a odd trig function. Well, what does that mean? What happens to the negative? Raphael's absolutely right. He says sine of negative theta equals negative sine of theta. For an odd function, you can simply pull that negative out in front. Okay. Well, let's go ahead and replace both the radius and theta with its opposite like we did. Let's simplify. So the opposite of the radius equals, now, if I can just pull this negative to the front, well, it's just going to make that 3 negative. So negative 3 sine of theta. And what can I do from here? Yeah, just cancel. I mean, both sides are negative, so you can divide by a -1, you can multiply through by a -1, but however you do it, the radius equals 3 sine of theta. See, I was able to get back to the original equation. So I know this particular graph, which is going to turn out to be the graph of a circle, is symmetric with theta equals pi over 2. Okay, with vertical line. Questions? Okay, well, there's only one type of symmetry left. We had symmetry with the polar axis, we had symmetry with theta equals pi over 2, and now we have symmetry with the pole. This is what we used to refer to as rotational symmetry. So if I had a graph, if I could rotate it 180 degrees and end up with the same graph, well, I knew it was symmetric about the origin. Well, here we're doing the same thing just with the pole. The test algebraically is going to be to only replace the radius with its opposite. So you'll notice there's something different for each of these. If we're testing with respect to the polar axis, we only replaced theta with its opposite. If we were looking for symmetry with theta equals pi over 2, we replaced both the radius and theta. Here, symmetry about the pole, we're only replacing the radius. Now, I don't have an example here, but I did go ahead and provide you a general form. If you go ahead and look at the bottom of that reference sheet that I gave you, that's the graph of what we call a lemniscate. Okay, it's going to look like a figure 8. Okay, right at the bottom. Now, besides really mentioning it here, we're not going to be able to do a whole lot with lemniscates. But if you were to take a look at the general form, what's going to happen if I replace the radius with its opposite? What happens when you square a negative? Yeah, you're going to get a positive. Okay, so the graph will remain the same. It'll still be r squared. Okay, so this guy does have symmetry with respect to the pole. Now, there's just one little note here. It's very important. If any of the symmetry tests fail, you may still see the graph show one or more of these symmetries when you're done. So, like, for example, this original graph right here. Let's say I'd plugged in negative theta, but simplifying it did not get me back to the original equation. These rules aren't absolute. Just because it fails the test doesn't mean you still may not see that symmetry after you sketch it. And in fact, a lot of these graphs may have symmetry with more than just one. You may see it symmetrical to both the polar axis and theta equals pi over 2 at the same time. In fact, you see a lot of that happening with roses. Okay? All right. So any questions about symmetry? Okay, no questions? All right. Well, let's go ahead and look at our first type of graph here, circles. Now, circles are going to be of a particular form, and we're only going to be looking at cosine and sine. Okay, so it's either going to be r equals a cosine theta, or r equals a sine of theta. Okay, so a couple things. Take a look at these first two graphs right here. You'll notice both of them represent a cosine theta, bless you, but what's the difference between them? There you go, the sign of that scalar value, a. If a is greater than 0, meaning positive, you're going to have a circle to the right of the pole. If a is negative, if it's less than 0, then your circle is going to be to the left of the pole. And you'll notice, even though in the equation we're using radius because that's how we graph those points, it's the diameter of the circle that's going to be your scale factor, okay, that length a. Okay, well, look at the other two graphs on the far right. You'll notice those are a sine of theta. Again, the only difference is the sign of that scale factor. If we have a positive scale factor, then it's going to be above the pole. If we have a negative scale factor, it's going to be below the pole. Okay, and that makes sense because at this point, you know, it's a really good rule. If you see cosine, you want to be thinking symmetry with the polar axis. Okay, remember we said the polar axis was the horizontal. So you'll notice both of those are symmetric with the polar axis. If I looked over here, when you see sine, you want to be thinking symmetry with respect to theta equals pi over 2. Okay, and that's exactly what we're seeing here. Now, there's just one thing. Anything but a 1 theta, and it's not going to be a circle. If that theta has any coefficient in front of it besides a positive 1, it is no longer a circle. Okay, so based on what we see here, if I were to give you this, r equals negative 15 cosine theta. Okay, that is the graph of a circle, but where would it be with respect to the pole? Would it be above, below, right, or left? Okay, well, I'm already thinking left or right because what trig function do we have? Cosine, so it has to have symmetry with the polar axis. Okay, now why are you saying left? Yeah, because a is less than that, less than 0. So you would see that the full length, the diameter of that circle should be 15. So I would probably see a graph that looks something like this, where that maximum distance is going to be 15. Okay. So really, like everything else in mathematics, it's just all about patterns and recognizing what's going to happen. Now, what if I were to give you this? This is a little off topic, but we're not going to be able to really do a lot with it, so you'll see why I'm bringing it up. 3 sine of 2 theta. Where would this circle be? Oh, what is that? Wait a minute, why is it not a circle? That's exactly right. This is what we're going to refer to as a rose. As soon as you put some kind of coefficient there in front of theta, it no longer becomes a circle, it becomes a rose. So kind of think of it as a flower. The scale factor is going to tell you how long each of those petals will be. That coefficient is going to tell you how many petals there are going to be. Okay, but there's a difference here. What you're going to notice is this one right here, all your petals are going to have a maximum length of 3 units. Okay, but this one would have 4 petals. Okay. If the coefficient of theta is even, you double that, and that's going to be the number of petals. Okay, so the petals would be 3 units long, and there would be 4 of them. What if I were to give you this? 5 cosine of 3 theta. It's still not a circle, it's a rose, as Aiden called it, because there's a coefficient in front of theta. Well, what's the maximum length of your petals? It would be 5, but how many petals would you have? There would only be 3. If it's an odd number, that's the number of petals you stick with. If it's an even number, that's when you double it. Okay. And I'll go ahead and go over that more tomorrow, but I wanted to go ahead and bring it up today because has anybody been looking at the review and noticed that problem? There is a problem on there where you have to get the correct graph. Okay. So hopefully that will help you out. But let's go ahead and graph one of these. Let's see what you think. Okay, now every one of these special graphs is going to have a couple of, I'll say, strategies or rules that you want to go ahead and follow as you attempt to sketch them. For a circle, you want to do these 2 things. Set the equation equal to 0 and then solve. Okay, and then 2, set the trig function. Now you'll notice it doesn't say the equation. It says set the trig function equal to plus or minus 1 and then go ahead and solve. Okay. Now, before we go ahead and get into that, we want to graph 4 sine of theta. So this is definitely a circle. How do we know that's not a rose? Okay, it's just 1 theta. Okay, there is no coefficient on theta besides 1, so it's a circle. Where would I expect it to be with respect to the pole? Above, below, left, or right? It'd be above. Aiden, why is it above? Okay, those two things. She says the scale factor is positive, and we have the trig function sine. So I want you to get in the habit, when you see a polar equation with sine, theta equals pi over 2 is most likely going to be its line of symmetry. Cosine is the polar axis. So length of 4, we're probably going to be looking at a circle that looks something like that, right? Okay. So let's see if that's what we in fact do end up with. Okay. So step 1, set the equation equal to 0 and solve. So 4 sine of theta is equal to 0. Okay, well, how do I solve this? How do I get rid of the 4? Just divide them out. Okay. So 4. So sine of theta is equal to 0. Remember, 0 divided by anything is 0 with the exception of 0 itself. Then it's undefined. Now, how am I going to find theta? What do I have to do to sine? We have to take the inverse. So sine inverse of 0 is going to give me theta. Okay, so now we have to think back to our restrictions. Kyle, can you help me out on this? What two quadrants was sine inverse restricted to? One and what? You're half right. One's correct. One and 4. There we go. Okay. Remember, it was restricted between negative pi over 2 and pi over 2. Okay. So sine inverse was going to end up in one of those two quadrants. So think about this. We're not going to worry about using the calculator. Think about all the ordered pairs that we have between negative pi over 2 and pi over 2. I'm looking for the one ordered pair where the y value is 0. What am I thinking of? It starts with a Q. Quadrantal. So what's the answer? Okay, so what's the degree measure at that location? 0. Okay, so we can go ahead and say 0 degrees or 0 radians. Okay, because at that location, remember you have the coordinate 1, 0. Remember, sine is the y value, cosine is the x value. Okay. All right, so that first one's done. Okay, we know that it's got to be 0 when I set the equation equal to 0. Now, for the second part, it says set the trig function equal to plus or minus 1. The trig function, not the equation. So my trig function is sine. So I'm going to say sine of theta equals plus or minus 1. Well, I've got to take the inverse just like I did a moment ago. Sine inverse of plus or minus 1 is equal to theta. Okay. So now, where from negative pi over 2 to pi over 2 do I have y values that are a positive or negative 1? They are the quadrantals. In fact, what are those? Pi over 2, negative pi over 2. Perfect. Now, is there one of those that I can get rid of? There you go. Remember, where did we say the circle was? It was up top. It was above the pole, right? So we could probably not worry about negative pi over 2. Okay. All right, so let's kind of think about why we did this. Set the equation equal to 0. Set the trig function equal to plus or minus 1. Now, I'll tell you, we're trying to find information about the radius. But can anybody tell me what is it that we're actually trying to find? This is actually telling me the locations where the radius is what? Where it's the longest or the what? What's the opposite of the longest? Shortest. But what are some words we like to use in mathematics to describe those? Starts with an M. Maximum and minimum. That's exactly right. By setting the equation equal to 0, you're finding all the locations where the radius is going to have its minimum length. So I know the minimum length of the radius has to be at 0 degrees. So by setting the trig function equal to plus or minus 1, what am I finding the locations for the radius to be here? If I've already found the minimum, then it has to be the maximum. This has to be the location where the radius will be its maximum length. Okay. And in fact, if you're wondering, why is it plus or minus 1, if we go back to the first semester, what was sine's period? How long did it take before it repeated itself? Not pi. 2 pi. It took 2 pi radians, right? So let's say this is pi over 2. Let's say this is pi. 3 pi over 2. And then 2 pi. Okay. Does sine start at 0 or a maximum? Sine started at 0. Now remember, sine and cosine both alternated between what values? 1 and -1. Remember, that's why on the unit circle, the maximum distance we can have from the origin is always going to be 1. Okay? So sine started with 0, then it went to a what? Maximum, then a minimum, and then a 0. Okay. So if I were to give you any trig function, how many people feel 100% confident you could graph it easily? Ooh, a few hands are going up. Okay. But do you see why we went ahead and set it between plus or minus 1? The original graph oscillates between that. So here, that will tell me where my radius will have its maximum length. Okay. So good, 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 good. Well, speaking of, let's go ahead and create this table here. Theta, the radius. Now, you can always put as many values as you want into the table, okay? But at some point, you're going to start to notice that the values are just going to repeat themselves. In fact, let's use the symmetry to help me out. Because it's 4 sine of theta, we know this guy has to be symmetric with the line theta equals pi over 2. So we really only have to plug points from half of that graph into my table. Okay, so let me show you what I mean. And for this first one, let's go with degrees. So let's start at 0. And then what are the degree measures we feel really comfortable with from the unit circle? Well, 60 is one of them, but we have 2 below that. 30, 45, then 60, and then we have 90. Okay. All right. So I want to go ahead and show you a couple things. There's a reason why I chose these points specifically, and if you don't already see it, I'll connect it for you in just a second. But take about 30 seconds, fill in the rest of that table. Now, 3 of these, I'm really hoping you don't need the calculator for. You shouldn't need a calculator for 0, 30, or 90. Okay, but we are going to need the decimal value when it comes to 45 and 60. So, like for example, the radius is going to be 4 times sine of 0. The radius is going to be 4 times the sine of 30. One at a time, you want to plug those in. The only decimals we should be getting are for 45 and 60. Okay, so let's see what you guys remember. Let me give you a few seconds to do that. Okay, let's go ahead. How about we start with, who have I talked to lately? Jasmine. I need 4 sine of 0. Yes. It is 0, because sine of 0 is 0 times 4. Okay. 4 sine of 30. Savion, help me out. Well, no. What's sine of 30 degrees? 2. Okay, we're close. No. Somebody want to help me out? What's sine of 30? 0.5, so 1/2, and then half of 4. That's 2. So were you telling me sine of 30 was 2, or the final answer was 2? Say final answer. There you go. Yeah, there you go. Okay. So that's 2. All right. Let's see here. Enzo. Let's go ahead and skip to the end. 4 sine of 90. That is 4, because sine of 90 is 1. Okay. Now, this is why you're going to need decimals on the others. Can you tell me what was sine of 45 degrees? Square root of 2 over 2, right? Okay. What was the sine of 60? Bless you. Square root of 3 over 2. Okay. So, Connor, what is 4 sine of 45 degrees? Let's say to 2 decimal places. Okay. I think I was getting like 2.83. Do you guys agree? Okay. There you go. All right. 2.83. And then I need, Satish, why don't you finish that off? 4 sine of 60. 3.46. There we go. Okay. So now I want you to go ahead and take a look, why we started this problem with those 2 steps. We set the equation equal to 0 and then the trig function equal to plus or minus. This gives me the locations for the minimum and the maximum lengths of my radius. We'll take a look. At 0 degrees, I got the smallest length of the radius. At pi over 2, okay, 90 degrees, I got the largest length for the radius. Okay. So that's what it's telling me before I even start my table. Okay. Well, the only thing is I've forgotten how to plot these points. Now, I do remember how to do the first one. At 0 degrees, the radius is 0, so that's just going to be a point right here at the pole. But let's say this is 30, this is 45, this is 60, and I'll just go ahead and change that for consistency to 90. Can someone help me out with the other 4 points? Remember, this is one of your last opportunities to come up to the smartboard. By the end of tomorrow, you don't want to go home and go, I have student regret. Oh, that's true. Satish is absolutely right. It's the last time we can use the random number generator. Thank you. Everybody's like, yeah, thanks, Satish. We appreciate that. Okay. Random number generator. There it is. Okay. All right, so we're going to go between 1 and 36. Okay, just last opportunity for someone to be able to say that they volunteered. Okay, here we go. It's generating. 8. I didn't choose you. The program chose you. You just have to plot those points. All right. Look how excited Jasmine is. Okay. So now you want to show me the point 30 degrees 2. Or 230 if you actually write it.
30 degrees and 2.
Yes.
Right there.
Okay. Perfect. And now we need 45, about 2.83. Okay. And then we need 63.46. Okay. And then 94. Perfect. That's it. See, look at the smile on her face. Big old smile. Okay. All right. So let me go ahead and highlight these just a little more. So she is absolutely correct. Okay. But this is what I was talking about, why it's important to know the symmetry of your graphs, because if I know that it's symmetric with theta equals pi over 2, well, what can I do with these points that she just plotted? Yeah, I can just reflect them over. See, that allows me to create a smaller table, so half the points, but give me double the coordinates. Does that make sense? Okay. Just saving work for myself. So I know that if I reflect it over, I've got to have a point here. I got to have a point maybe right here. And you notice horizontally, they've got to be even. Then I got to have a point right about here. Okay. So that when I go ahead and connect them, there's my circle. Well, thank you. Of course, it should be the final lesson of the school year that everything finally comes full circle. No? Okay. All right. Questions. How you doing? Okay. So circles aren't too bad, right? Okay. Not too bad at all. Good, good, good. Okay. Well, the last thing I'm going to go ahead and show you today, now we won't graph any of them, but I do want to introduce limacins. Now, they're going to be of the form a plus b, a plus or minus b, cosine of theta, or a plus or minus b, sine of theta. You'll notice theta still has to have that coefficient of positive 1, but now we're adding or subtracting that trig function to some other value. Okay, the thing about these two values, even if you're subtracting, we still view it as a positive number. Okay, now there are 4 different types of limacins. So depending on how the two values relate to each other, well, that's going to tell you what type of graph you're going to get. You're either going to have a limacin with an inner loop, so it loops back into itself, a cardioid. This is what we call the heart-shaped graph. Okay. We have a dimpled limacin, and then we have a convex limacin. So at first glance, you're probably not noticing a whole lot of difference between the cardioid and the dimpled limacin. Okay, but there is a difference in how you graph it. What?
Like the 2008 election, dimpled and pregnant Chads.
What? Dimpled and pregnant Chads?
So in Florida, you like punch the ballot, but people with like with a little stick thing.
Hanging chads? That's in the 2000 election. It's hanging.
Oh, it was 2000.
Hanging
Well, no, dimpled.
Hanging
pregnant
chads?
2 other classes. I guarantee it. You can look it up. Dimpled, pregnant, hanging.
Why does any of this matter?
It was very important. Okay, that's that.
Okay. I'm gonna miss you, Jack. No, seriously, I really am gonna miss you. You know, like I said the other day, the banter between you and Skylar is just very amusing. Who said tragic? Raphael? Okay. All right, anyways, the difference between cardioid and dimpled is that when you draw a cardioid, it actually comes to a point. So, like, it'll come out like that. It'll actually come to a point when you finish it. But with a dimpled limacin, it's not going to come to a point. It's just going to look like someone actually kind of poked one side of your circle. So maybe something like that, just like a little indentation. You see how it doesn't come to a point? That's the difference between the two graphs. Okay, and then your convex one here, one side of it actually straightens out. Okay, becomes linear for a short time. I always kind of think of it like this. Have you ever played with some Play-Doh? You rolled a ball and then you put it on a table, flat surface. Well, when you pick it up, that one side that was on the surface, you know, it's like flat. So if you were to look at a cross section of that, okay, that's what we're talking about when we say convex. So let me give you an example. Okay, let's say I were to give you something like 7 minus 2 cosine theta. And it doesn't matter if it's cosine or sine. That has no bearing on it. It's the two values that you have. So I know right now there's no way this is no longer a circle because we are subtracting this from another value. Now, if it were just 2 cosine of theta, where would it be with respect to the pole? Above, below, right, or left? That would be a circle. See, it would be symmetric with what? The polar axis or pi over 2? Polar axis, because it's cosine. It's positive, so it would be to the right. But the fact that I'm subtracting that from another value, it's no longer a circle. It's what we call a limacin. Now, we want to go ahead and figure out which of the 4 types of limacin it is. So what's A? A is 7. What's B? 2. Very, very important. Whenever we compare A and B, we only look at the positive value. Now, when you simplify the equation, you definitely go ahead and include the negative, but identifying A and B, they are always positive, no matter what. So let's just run through the list. Okay, is 7 less than 2? No, so this would not be an inner loop limacin. Does 7 equal 2? Nope. Okay, now let's fill this one in. 2 is less than 7, so it's looking good so far, but is it less than 2b, 4? No. So just by process of elimination, has to be a convex. So A7 is greater than or equal to 2B4. Okay. Now the orientation might be different, okay, depending on what you have in your equation, but it's going to be a circle where one side of it's flattened out. Okay. Now if we go through the list of these right here, we're going to notice that this one here, 5 plus 2 cosine theta, because A is larger than B, that's going to end up being another convex limacin. Okay. This one's convex as well. Okay. What do you think about this second one right here? 2 plus 5 cosine of theta. That would be an inner loop. Okay. A is less than B. Okay, so this is an inner loop. Okay. And what do you think about 5 plus 5 cosine theta? That's a cardioid. That's the heart-shaped graph. What tells you that? A equals B, 5 equals 5. So this is a cardioid. There you go. So being able to identify it just by looking at it, really easy. Is anybody not sure how we are doing that? What's that, sir? Easy what? Collapse. Is that more speak? So that's what's popping? It's straight up bars? No? So does identifying limacins straight up smack?
Yes.
Or what was it? It just smacks. It smacks. Because Zach told me the other day you got to make that noise too. It smacks. Just in case anybody's wondering, that is Zachary Schmidt who told me that. All right, well, that's as far as first period got, unless you guys just want to continue to talk about teenage language nowadays. We're done. Susie's okay? All right. Okay, so we will try to get as far as we can tomorrow.